we are now recording. We got the slideshow in the right place. So let's go from current slide, and let's even march the key here. All right. Now, sort of the latter part of the alphabet doing pretty well, or the last part in the middle. The first part, wow, nobody here. Okay, we are recording. Any questions on anything we've done up till now? Okay. That's not the key I want. Well, I do. Okay. This is the one I need. Okay. Now, why all this stuff about derivatives? Are they any good? Any purpose for them? Or sure, lots. Okay. You wouldn't have invented them if they hadn't been. But one of the things we use them big time for is to show the behavior of a graph. Here's a function. F of t is equal to t cubed minus 12t plus 4. Now, before you get all bent out of shape, not that you would get bent out of shape, but seems like we've seen this one before, right? Is this the one? I think that was the last one we did. No? I think the slides and the graphs are different. Okay, let me see. Yeah, we did that one already. Sorry. Here's the one we're looking for. Okay, let's build on this one. Okay. This is figure 4 in your text on page 126 or somewhere thereabouts. Okay? Now, here is a function. F of x equals x cubed minus 12x squared plus 36x minus 16. Now, just a quick glance at that. That's not an odd function, not an even function. It's a neither function. It's a polynomial, but it has both even and odd exponent terms in it, so it's a neither. Okay, now what does the, there's the graph of the function. What do your derivatives tell you? What is the derivative of a function? What does it relate to? Slope of the tangent line, exactly, okay? So, anywhere this function is increasing, the slope of the tangent line is positive. Easy to see on the graph, obviously. When it has a turning point, you have a zero slope. When you have going a decreasing function, negative slope, another turning point here, the slope is zero again, it goes positive, it means the function is increasing. So, what we can learn from this, without drawing the graph, if all you do is take the first derivative of this, set it equal to 0, you'll find that will be there and there. We'll do that in a minute, maybe. Okay? And when we, on the left side of this one, we can do a sample point, like 0 or 1 or whatever, and find out it's positive there, and that lets you know it's positive anywhere in between the zeros. Now this is for a smooth, continuous function like a polynomial. In between these two, pick a point. They picked 4. The derivative there is, they didn't pick 4, they picked 2 values there. I would have picked 4, found out the derivative is negative there, meaning the slope is decreasing in between these two zeros. And outside of this 0, I would have probably picked 7, maybe that's what they chose, and see that the derivative is positive there. So you can learn a lot about a function without graphing it. The derivative helps us to see that. Okay? Now, what they've done here, this is a function. No, I'm sorry. Yeah, it is. Okay. Take a derivative of this function. What would that be? Derivative of that function. 3x squared minus 24x plus 36. That constant term gives you nothing in the derivative. So 3x squared minus 24x plus 36. Now, I think they slightly mislabeled this. If I think they should have labeled this. Oh, I can't write on it. Okay, I'll leave it alone for now. They should have labeled this y prime. If that's y versus x, this is a graph of y prime versus x. Because you see here at x equals 0, that's a very positive number. The slope is. So you start up here for y prime. Okay? And it continues being positive, but becomes less and less positive till it reaches 0 right there. So where the first derivative is 0, this is a graph of the first derivative. Where the first derivative is 0, the slope is 0 here, first derivative is 0 there. Okay? Then the first derivative turns negative, so you're negative here. And this is sort of hard to see. We'll get to it later. Okay? You'll notice here the first, I don't know if you'll notice, but it's true. All in here, the curve is like this, so the tangent is on the outside of the curve. Okay? But somewhere down here, it gets on the lower side. This is on the upper side of the curve. This is on the lower side of the curve. We'll talk about that later. So somewhere in between here and here, it went from being on the upper side of the curve to being on the lower side of the curve. Don't sweat that yet, but I'll tell you right now, that's that point right there. Looks like we're x equals 4. Okay? Because the first derivative is decreasing here, but it's negative here. That's the big thing here, negative. But it becomes less negative, goes to 0, and then goes still less negative until first derivative is less negative until it reaches its minimum here, and then still less negative until it goes back to 0 here. Okay? And then from here on is positive. Okay? But guess what? Your first derivative here, what do we call that function there? What kind of function? Polynomial function? Maximum exponent of 2. Second? It's not even because this one is a 1. Maximum exponent of 2, we have a special name for that kind of polynomial function. Sounds like it has something to do with 4, but it doesn't. Maximum exponent of 2. Quadratic. It's a quadratic function. What's the graph of a quadratic function always? The shape. Parabola. And sure enough, that looks like a parabola. And since that is a parabola, you see it never comes back down again. Parabolas just keep going in the same direction. So this is, no matter how far you go here, your slope's always going to be positive. No matter how far you go there, the slope's going to be positive. And it gets to be a larger and larger positive number. It gets to be steeper and steeper and steeper. Never reaches infinity, but it never slows down in steepness. Okay? So you can tell a lot about the function here by looking at its derivative and studying its derivative. So the derivative is 0, that's where you have a turning point on the polynomial function. Where the derivative is positive, that's the increasing function. Derivative is negative, decreasing function, and positive again. So there's lots and lots you can tell about the behavior of a graph just by looking at, and I think we just did example 5, didn't we? Okay, sorry about that. That was example 5. Okay. Now, they haven't introduced the terms yet, so I'm going to hold off from that. Okay? But the big deal here, the derivative of the function gives the slope of the tangent line, and that indicates where the function is increasing, decreasing, or at a turning point. Okay? So those are the big ideas there. Okay, I think we've already talked about the rest of it. Let's do example 6 this time. I forgot to do, I don't know if they, yeah, they do have a curve for it. Oh no, this is the rest of 5. This is what we talked about. And let's see how they verbalize it. We did. See what they do. Okay, this is the f prime we had here. When we look at f prime of x, we see the first derivative is 0 anytime x is the first derivative is negative only in between 2 and 6. We saw that in the graph down here. We saw it in the slope of the tangent line there. Tangent line has negative slope between 2 and 6. The derivative at 2 and the derivative at 6 is 0. That means you had a turning point at 2 and a turning point at 6. Tangent line was horizontal there. Now, let me rephrase that. You can have a horizontal tangent line and it not be a turning point. In this case, it was. Okay, we'll see some later that are not. They're sort of special cases. And then we see the derivative was greater than 0 or positive for all x is less than 2 and all x is greater than 6. So that means increasing function in those 2 places. Okay, so we can get a lot about the graph of a function without graphing it, just by analyzing the first derivative. Okay, and basically, let me remind you, first thing we did, set it equal to 0. Don't name that tune in just a few bars, but not yet. Okay, so let's blow this up for now. No, let's not. Okay, let's do the function. Identifying the derivative. Oh no, they don't give us any function. Let's blow them up. Okay, sorry about that. Thought they were going to give us some functions and we were going to play with it. Okay. The graph of f is shown in here. There's some function f. Now, which graph, b or c, is the graph of its derivative? First derivative. What you think? This is the function f of x, the blue graph. Which of these is the graph of its derivative? And again, I would call those y primes. I wouldn't call it y because y is what the function is. That's the graph of y prime, not the graph of y. Say again? C, you said? That means yes in Spanish, right? Okay, never mind. Okay. All right. Yes. Why do you say C?
Well, first I guess, and second.
Oh, okay. Yeah, okay.
Because the center of the graph is 4, so I'm guessing that would be where they touch the center.
Okay. So he said the center of the graph is at 4, and what's special about 4?
It's the center.
Okay, it's the center, but what do you mean by that? Halfway between 0 and 8? Okay, but what do we mean by that? What were you looking at? Just looking at the center. Okay. That's a turning point, exactly. 4 is a turning point, okay? That's what you were meaning, right? Yeah, okay. Now, what does that mean? On one side of that, think tangent lines, folks. That's why they drew them here. Tangent lines relate to the first derivative, right? Positive slope on the left side, 0 there, negative on the other side. If this is a graph of your derivative, you're a positive here on both sides of 4. Can't be. Should be positive this side, 0 here, and you got it exactly right there. It's positive on this side, negative on this side, and the slope is 0 there. That's a dead giveaway. Another thing, look at the very first tangent line here. What's that function doing there? It's decreasing, so the first derivative is negative. This first derivative is positive here. That one's negative. Okay? Here's another turning point or place where the first derivative is 0. So you need the first derivative. Well, that's fine here and here. But see, it's the wrong direction here. Okay? And then we got this. We have another 0 at 7. Well, both of those have zeros at 7, so you can't tell anything there. But what you notice here, beyond 7, increasing function, which tells you what about the derivative? Positive. This has a negative 10 first derivative here. This is positive. Surely C is correct. My guess or not. Okay. All right. Any questions on that? Does it make sense? Okay. All right. All right. Good deal. Okay. Why is it not advancing? There we go. All right. I don't know how far it advanced. Okay. This is the little table you see talking about that. Wish they'd be on the same slide that you can look at it when you're reading it. In the book, it's on the same page. But what we saw here, you had negative slopes of the tangent line at the very beginning, 0 to 1, and again from 4 to 7. Okay? You had zeros of the slope of the tangent line at 1, at 4, and at 7. Okay? You had positive slopes between 1 and 4 and beyond 7, and therefore, yeah, that made C the correct answer. Okay? Make sense? All right. And again, where I would begin, finding the zeros. Then you look to the left, look to the right of each 0, see what the slopes are there. That's what they were doing. They haven't told you that yet. All right. So here's Theorem 5. It's Theorem 5 in our text, Theorem 3 in the old edition. They talked about two things but didn't name them theorems. In the new edition, they named them theorems. Okay. Jumping another rabbit here, okay? That's a phrase I learned from my mom. Her mother was quite a character, I think. Hard worker. But boy, when she ever sat down to get to talking, Mom said she could just run a subject into the ground. And she had an aunt that was not much older than her, and she called her Aunt Nat. Aunt Nat would come over to visit sometime, and my grandmother's name was Nora, and so they get to talking in rural North Carolina. That became Nori. And grandmother would just go on and on and on about this topic. And finally Aunt Nat would say, "Hey, Nori, let's jump another rabbit, okay?" You know what I mean? Pick some other topic to talk about. Jump another rabbit and start chasing it. So we're going to go to a brand new rabbit here, okay? The number E. Anyone know what the number E is? It is a number. Some feature of that number, totally irrational. That has nothing to do with gender, of course. But no, I didn't say that, did I? Okay, so what do we mean by an irrational number? A rational number is any number that can be formed as a ratio, rational ratio, of two integers, as long as the denominator is not 0, okay? But any two other integers, positive, negative, anywhere, that's a rational number, okay? Irrational number can't be done that way. Now, that's sort of hard to do, so another way to refer to it, a rational number, if you write it in decimal form, is either going to terminate at some point, like 0.25, 0.75, 0.125, something like that, or it's going to repeat some pattern after a while, like 0.33333, that's 1, 0.787878, 0.257575757. As long as somewhere down the road there you start repeating a pattern, that's a rational number. E is not rational. Here's the first 4 digits of it, and you could write the first 24 digits of it, and you'd never see a pattern. 84 digits of it, you'll never see a pattern. 104 digits, you'll never see a pattern. It never produces a pattern. Can anyone think of another irrational number? Pi, of course. Okay? 3.141559, it never repeats a pattern. Those are the only two. About square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, square root of 10. All those are irrational numbers. Cube root of 2, cube root of 3, cube root of 4, cube root of 5. All those are irrational numbers. Okay? There's tons and tons of irrational numbers out there that can't be written as this is one, E. What's special about E? Just one of those irrational numbers, right? Well, it forms the natural base of our number system. Now, we may have thought our base of a number system was 10 because we have 10 fingers and toes or whatever. That's how we wanted to count, so we made sure. Numerically, we use base 10, adding, subtracting. We use it all the time. But in calculus, suddenly it emerges that E is the natural base of our number system. But it's an irrational number. Now, one of the people, several people I think had toyed around and played with it, but I think the first one really to identify it, name was Euler. Okay? So that's spelled E-U-L-E-R. And that, I think, is why it got named E. Either he was sort of, felt special about it and wanted to name it after himself, or maybe someone later did. Okay? But that's the natural base of our number system. And here is why it's my favorite number in calculus. Because if you take derivative, and by the way, now, here's another sort of strange feature of it. We count it as a function, too. We count it as the exponential function. It's not the only exponential function. An exponential function is some number raised to some variable power. That's an exponential function. 2 to the x, 7 to the x, negative 4 to the x. Those are, well, actually, we don't usually use negatives in the base, but those are all exponential functions. But this is the exponential function because of this one feature right here. The first derivative of e to the x is e to the x, okay? I'll do that one any day, okay? I don't have to remember anything itself. Its derivative is itself, okay? Now, that seems pretty simple and straightforward. A lot went into finding that out, though, okay? They do a little proof here, and this proof is a pretty good one to look at, okay? They do make some assumptions here. We'll take for granted a few plausible facts whose proofs are somewhat technical, okay? The first fact is that f of x is equal to b to the x, where b is any number raised to the x power exponential function, is differentiable for all b greater than 0. Notice what I said, the base, we usually don't use negative numbers there. And the other thing, we don't usually use the base of 1, because 1 to any power is still 1. So we don't use 0, we don't use negatives, we don't use 1. But any other base would be perfectly fine. Now, they're telling you it's differentiable. Fine, very good. Assuming this, let's take a derivative, okay? Now, I don't know, I don't usually do this proof here, but because several things depend on it, and it is tedious, and it sometimes feels like you're running around in a circle or you don't know why you're running anyway, but let's give it a shot. So here's your function, f of x is equal to some base, not negative, not 0, and not 1, raised to the x power. That's an exponential function, okay? They've told us already it's differentiable, so we can proceed. What's the formal definition of a limit? I mean, of a derivative? I gave it away. the limit as, they're going to use h, I believe, right? H approaches 0 of f of x plus h minus f of x divided by h. Okay, that's it. Okay, now let's plug in our b to the x. Okay, that's the limit as h approaches 0 of, now what is f of x minus h? That's, my writing sort of stinks here, but okay, x minus h. It doesn't look good, so I'm going to try to clean that up a little bit. Yuck, my eraser's not working either. Still not working. Still not working. There it comes. Okay. All right. F of x minus h. No, x, that was a plus. X plus h. Yeah, sorry. Yeah, that's it. Okay. So what is, if f of x is b to the x, what is f of x plus h? Everywhere you see an x, put an x plus h. B to the x plus h. Got it. Okay? So that's going to be the limit of b to the x plus h minus, and what was your f of x? B to the x, right? Over h. All right. Now, going to have to do a rollback here, okay? I want you to try to remember what our rule for an exponent, if you have a base, a sum of two exponents, what's that the same as? You usually think of it the other way, but think of it backwards now. Give me a number, any number. 2, okay? Now let's raise that to, give me another number, any number. Boy, y'all are stuck, aren't you? Plus, give me another number, any number. 1, all right. Okay, that's 2 to the 2 plus 1. Okay? Anyone tell me what that is? 8. Now, if you take this 2, raise it twice, and then do a 2 to the first, and multiply those two together, what do you get? 8, yeah. Anytime you're multiplying same bases, different exponents, keep the base, add the exponents, right? You've done that. So we're going the other way. If you have a base with the sum of exponents, then you do the base with that exponent times the base of this exponent. If that was a minus, you would be dividing by the second. Okay? So with exponents, additions become multiplications, subtractions become divisions. That's the whole principle, and y'all don't even know what this is, of a slide rule. Any of you have even heard of a slide rule before? Oh, you poor people. Okay? So you've grown up with computers and calculators. Now, this may be hard to believe, but when I was in college, a sophomore in college was the first time I even saw a calculator. Okay? It was a physics class of about 200 people, 8 o'clock, first morning of fall term, my sophomore year, 200 people or so sitting in a lecture room, and here came two guys with this big old box strapped to their lecture. We'd all heard about them, but these two guys had them. And you know what we said? There goes the curve. Because the rest of us in physics classes or other things that you required lots of complex calculations, you use slide rules. And what a slide rule was and they have several kinds, but the simplest one was a thing with two scales, and then a sliding scale in between. That's why they call it slide rule. Okay? And what you do, it was all log scales. And the log scales, you'd find the number on the log scale, like 483. Okay? You're trying to multiply that by 5,210. Okay? Can't do that real easily on pencil and paper. You can do it, but if you, on the fixed scale, found your 483, and that would be 4.83, or you estimated it there, on your log scale, move the slider there until zero is there, then find the 5,200. What you had to do is keep up with scientific notation. That's why it was really important. 482 was 4.82 times 10 to the second. 5,000, whatever I said, that was the 5 point something by times 10 to the third. So you would find that, add that log to it, find the 5 here, put the 0 here on the 4, okay? Go over here, and then you read your answer down here at the right power of 10. 2, 3, that would be times 10 to the fifth, okay? That's how you did complex multiplications. Divisions, you did it the other way, you subtracted them. When you tried to raise numbers of powers, there's a way to do that, but you did everything on the slide rule. They were rulers about a foot or so long, and things, some could be longer or shorter, but your numbers got harder to do. You could usually only get 2, maybe 3 digits of precision. That's all, folks. Okay? And walk these two guys with calculators. And he said, there goes the curve. Because all they have to do is push buttons. We have to manipulate the slide rule, keep up with your exponents and that kind of stuff. Now, why did only 2 people in the room of 200 have have calculators? And by the way, those calculators could add, subtract, multiply, and divide. Okay? They really could. And guess how much those calculators cost? $600. I couldn't afford $600 for a little box. And guess what? You also had a cord with it. You had to sit somewhere you could plug it in. It didn't have a battery that's held any charge at all. You had to be plugged into a cord. So here, the box, cord, and everything else, and but boy, they had it not. Okay? So, that was the basis for slide rules. Multiplications became additions. You just had to keep up with your base and your exponents. That kind of stuff. So, let's go back to the problem at hand. What would b to the x plus h be then? You forgot we were doing this, didn't you? Okay. The limit as h approaches 0 of b to the x plus h would then be b to the x times b to the h minus b to the x divided by h. Right? Okay? Now, that numerator is all right to leave off the limit for a while. I'll put it back in later. I'll just get tired of writing it. Factor out the b to the x, and that leaves us a b to the h minus 1 over h. Okay. Well, I really need the limit in there. Let me write it. Limit as h approaches 0. Now, here's another little thing that you can do. The limit is dealing with the h's. So it's not dealing with the x's at all. So therefore, you can pull that b to the x on the outside. Okay? And that becomes b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Now, you still can't do the division there, but you can do that. Now, hang on to that concept because I'm going to go to the next slide, and this is that next slide. And again, it doesn't do a lot for me to do this, but this is what they do. They say this now is a function of b. M is a function of b, y, of this mess, okay, that limit that we just had here, okay? What we're looking for is what is that M of B. Now, obviously, we don't know if that has a limit. We're assuming it does because they told us it was differentiable. But what would that be? Because see, as H goes to 0, what's B to the A? B to the 0. 1 minus 1 is 0 over 0. That's an indeterminate form. No guarantee it has a limit, except they told us it was differentiable, so we know it does have a limit. But we don't know what it is. So the rest of their proof here, they're going to be trying to figure out what is happening. Okay? Now, if you let that rest as that, going back here, remembering that I'm sorry. If f of x is this, f prime of x is equal to that. And we brought that down to here, and the next slide has this is m of b, so basically where we get to then is this. D by dx, or f prime of x, okay, f prime, is equal to that m of b times b to the x, okay? Because this was that limit part, and this was the factor b to the x on the outside. So if you follow that going along here, fine, okay? Before continuing, let's investigate the m of b numerically. So that's what example 7 is, okay? What they're going to do is estimate m of b numerically for b, certain values of b. And here's the values of b that they're going to use. And that, like I said, they take so many detours here, you forget where you were heading in the first place. They just said, let's take b equal 2, then 2.5, then 3, and then 10. Why 10? I don't know. Okay. So, we're going to look at different h's for these values of the b. Okay? The base. The h is getting closer and closer to 0. Let's see where this is heading. Well, if you plug this stuff in, remember here's your m, and you're going to have an m of 2, h of 2, and we're going to figure out what it is. So when you plug in the point 0, 1, you get this number. 0, 0, 1, you get this number. Well, it looks like it's good to 2 digits here. 0, 0, 0, 1, looks like you're good to 3 digits there. 0, 0, 0, 0, 1, it looks like you're good to at least 4 digits here and getting closer. So we're going to round that, and why go through all this and then round it to this? I would say let's round that to 0.6932. Okay, well, 693 anyway. They do 695. I don't care. Okay, let's get another number, 2.5. Okay, plug that in, do the math for these h's, 0.92, 0.916. That's good, basically the 2 digits here. 9163, almost 3 digits there. 9162, looks like we are at 3 digits, so they rounded to 0.92. I don't know why. I would say 0.916. I'm sorry, 0.916. I would say. I would give it one more digit. So let's go up to there. 2, 2.5, 3. At 3, we have plug that in, 1.10, 1.09. So that's good to 1 digit here. 1.098. That's good to 2 digits here. Actually, those are 2 digits here too. Okay. 1.98661. That's good to at least 4 digits here. Okay. So they say 1.10, which you had almost at the beginning. Okay. Now, for some reason, they jump up to b equal 10. When you go to b equal 10, you get, and plug in those h's, 2.3293, 2.3, so good to 2 digits here. 230, almost 3 digits, not quite. 2302, that looks like you got to 4 digits here. So they rounded to 2.3. Okay, 2.30. Does this say anything special to you? Well, the only thing that's of importance here to me is somewhere between 2.5 and 3, that would be equal to 2.5 and 3. You had a value for this function, m of b, to be 1. That's the key. Somewhere in between 2.5 and 3, it became 1. Okay? Now, they do show the number e at the bottom of the page here as 2.7182818828. Look at that. Is that a pattern? Not quite. Look at the next digit. 45904. No, the pattern falls apart. It looks for the first, 9 digits, as if you might have 10 digits. You had a repeating pattern of 1812. 1828. Okay? Until you get to the 11th digit and it's a 4. No more a 1828. It's a 4 or 5, and then they just are random from there on. So nope, it came close to looking like it could be a repeating decimal, but it wasn't. Okay? That number e is the place where that m of b is equal to 1. Okay. So what's the point? Here's kind of the point. As you put other values in here, here's 2 to the x. By the way, whenever x is 0, this y is 1. Because anything to the 0th power is 1, except 0, but we're not having a base of 0. Okay? So, all these pass through that. So when x is equal to 2, b is equal to 2, you go up there. B is equal to 2.5, you go up a little steeper. It's flattered. Okay. The 2 to the x is flatter down here, or higher, larger here, smaller there. Goes up more slowly. 2.5, flatter, lesser here, goes up more sharply there. 3 goes up even sharper. And somewhere in between 2.5 and 3, you have that irrational number e, and there you have another curve that looks just like the other curves, with this exception. The derivative of that pink curve everywhere along it is itself. The others have a factor, a little bit of a factor that's not quite the same. But e to the x, that factor is 1. Okay. They grow steeper as the b's increase past x equals 0. They're steeper and steeper and steeper. And somewhere in between there, you get a e to the x, which is that irrational number. Okay. That's, I think, the graphical insight they have here. Let's go to example 8. Okay. Find the tangent line to the graph of alpha, well, here it is right here. Alpha of x is equal to 3e to the x minus 5x squared. Okay, I won't write it again then. It is pretty small. Can y'all read it from where, if you don't have a book? Can you see that? Here's your alpha of x. Okay? Now we want find the tangent line. Now when they say that, what are they looking for? What is your answer going to look like? When they say find the tangent line. It's not, oh, there it is. No, that's not what they mean, find the tangent line. Okay? Good first answer. Okay, here, you're going to take a derivative. But what is you looking for? What is your answer going to look like when they say find the tangent line? An equation, and basically how will that equation look? Second? No, that's your derivative. An equation. What does an equation of a line look like? Okay, you're going to have the slope in it. That's where your derivative comes from. Say again. What will it look like? Your answer. Equation of a line. No, the equation of the line. A line is a straight line, by definition, right? Okay? Equation of a line is going to look something like this. Y is equal to mx plus b. That's the simplest equation of a line. Did you say that already? Okay, I can't hear you. You have to speak up. Sorry. Okay? So that's what it's going to look like. Now, there are other equations of a line. Usually we'll use those before we get to this one. Can you give me another that we might use before that one? Point slope, and what would that be? Got it. Okay. That's the one I think we'll use first, but then ultimately we'll go that way. So that's what we're looking for. So we're looking for two things here. Okay, what does that x1, y1 mean? Okay, it's a point on that line. Okay? So that's a point, and m is the slope. And slope is related to derivative. Very good. So here's your function. What do you think the easiest, and by the way, they say, find the tangent line to the graph at x equal 2. That's our problem. Okay? You got two things to do. Find the point and find the slope. I don't care which one you do first. You tell me. How do you know you've got a point? What does a point look like when you write it down? An ordered pair. Very good. Okay? And what's in that ordered pair? An x and a y. Guess what you got already? The x. So what's one step you can do? Find the y, plug it in, just like Glade. Okay, because f of x is equal to y, right? So the first thing, or one thing you got to do is f of 2 is equal to what? 3 e squared minus 20. Perfect. Now that doesn't look like a number, but that's a number. E is just a number, okay? 2.71, blah, 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 it goes on forever. You can square that number. In fact, on your calculator, you'll find somewhere on there the E key. And if you put e to the 1, that's e, you'll find that 2.71, blah, 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 blah. Okay? And when you press that key and then square it, or just press that key and put a 2 by it, you'll get e squared. Okay? And you can do 3e squared minus 20 and get that. But that's this number. So that's your y1. This is your x1. So you got your point. What other thing do you need? Slope, and how do you get it? Take a derivative. So let's take a derivative. F prime of, yeah, we'll do x first, yeah, is equal to a little louder. I couldn't hear. I saw your mouth move. No, 3e to the x. It doesn't change anything. E to the derivative of e to the x is e to the x. Okay? That's why I like that one. Minus, what'd you say? 10x. You got it. Okay, but we're just not interested in any old f prime of x. Where do we want this? at x equal 2. So f prime of 2, which is the slope of that line at the point where x is equal to 2, that would be what? Three e to the 2 minus 20. Oh, look at that. It's the same as our, and this is a little bizarre. They're not always going to come out that way. They just did this on purpose to make you think it's going to be this easy, but it really isn't. Okay. So what we do now is, and by the way, that is your m. So what we have now is y minus, and what was your y1? 3e squared minus 20, I'm putting it in parentheses because it's just one number, is equal to, and then guess what? Same number, shame on them, 3e squared minus 20. They all will not come out this way, don't think it will, times x minus 2. Okay, I know what x1 is. That's our 2. Okay. All right, so what do we have? Y minus, let's go on and clear those parentheses, 3e squared plus 20, right, is equal to, and let's, boy, that's a pain in the neck, isn't it? Let's FOIL that and see what we get. 3, well, no, let's not. Let's just keep it. 3e squared minus 20x minus, now let's do the 2 here, minus 2 times that. That would be what? This times that. 6e squared. 6e squared. Plus 40. Does the minus change the sign? Okay, get it. Okay. Now, if we want it to get it to this form, we want to isolate the y, right? Okay, so we're going to add 3e squared and subtract 20 from both sides of the equation to get y by itself, the naked y there. So that's going to be plus 3e squared minus 20. Okay, let's see what that gives us. Y, because these go to 0, that's why we did it, is equal to, here's your slope, 3e squared minus 20 times x minus 3e squared plus 20. Yeah. Okay. Now, what they do in the book here, except seems like there's one of these is wrong number, isn't it? Oh, got it. Here's what they really did. Y is equal to 3e squared minus 20 times x minus 3e squared minus 20. If you put it in parentheses, it's that. And guess what? That's the same number. Don't even think that that's always going to be the case. It isn't. This is just a rare instance that it is. Someone with a calculator, figure out what this is. I'll give you a guess. E being a little bit less than 3 squared is going to be a little bit less than 9. So let's just call it 8 for now. 3 times 8 is 24 minus 20. It's going to be close to 4. Not exact, but fairly close. What do you get? You got the calculator? Okay, that's what they got too. I said fairly close. It doesn't have to be real close, okay? So 2.17 actually is what they use in the book. So y is equal to 2.17x. I'm going to put an approximate equal to because it's not quite, minus 2.17. Don't even begin to think it's always going to come out the same number there. It won't, it won't, it won't. Okay. Now, we've got the answer here. What I'm going to do is erase parts of this, okay? The reason I'm erasing so we can see the graph. Okay. Now, I wish I had written that so it would get included here. Don't think it's going to make, oh, they got it there, don't they? Okay, so I don't have to do that. Okay. Here then is the cubic function, oh, not cubic function, exponential function we started with. It's a mixture of exponentials and polynomials. But let me tell you this. Exponential functions are smooth and continuous. Polynomial functions are smooth and continuous. So you have a pretty good idea this is going to be smooth and continuous everywhere. So let's find the slope of the tangent line when x equal 2. There's the point where x equal 2. That's something a little bit greater than 2, 2.1, no, yeah, 2.17, okay? And its slope just happens to be 2.17 there as well. Don't think that's going to be the general case. Now, if you extended this line down here, the y-intercept would be at minus 2.17, okay? So, yeah, and that looks like that would be the case. -1, -2, just past -2. Looks like the case. So, yeah, looks like that's right. Okay? Now, I don't want to graph a function like that. I don't know if you can find any places that land on the tick mark, except that x equals 0. That works out pretty nicely. Because x equals 0, e to the 0 is 1. 3 times 1 is 3, minus 5 times 0 squared is 0. So that's just going to be 3. So that's the one and probably only place that's going to cross at a hatch mark. Okay? Period. All the rest of them are going to be irrational someplace or another because e to the x is irrational. So I don't particularly want to graph that function. But if I did, you can get, you see, you can find the slope, you can find the equation of the tangent line just by taking derivatives and evaluating. Okay. Make sense? They have a little conceptual insight there talking about b to the x and then letting x be a rational number and doing a variety of things there. I'll let you read that. I don't see anything necessary there for what we're going to be doing later. If I found out I'm wrong, we'll go back and do that, but I don't see that there. Okay. And here we have another issue. And I'm not really sure why they brought this up either. Well, yeah, I do. Differentiability, continuity, and local linearity. We've been talking about differentiability, fine. I think we talked about continuity on the limits chapter, so that's good. Local linearity, I'm trying to remember if this is the first time we've used that term. I can't recall. I'm teaching 3 math classes and two physics classes, 1 physical science classes. I can't remember what we talked about in each one. But here is a function that is a discontinuous function. Has a jump discontinuity that you can't resolve. Here the function as x approaches c is approaching some value here but never gets there because at c it jumps up to here and the function then goes downhill from there. This is all one function. It has to be a piecewise defined function. Has a jump discontinuity, so you we know already the derivative doesn't exist there. Okay? tried to do secant lines, say between this point and that point, it would be this green dotted curve. Between this point and that point would be that one. This point and that one, that one, that one. But if you tried to do discontinuities this way, secant lines this way, you would have these 2 points that would give you that one and this one. Well, the limit of these blue ones is your red line here. There is no limit that you're reaching as you get closer and closer here, except the vertical line, which is a line. It's not a function. So that's the problem that we get at discontinuity, at discontinuous functions. You can't have derivatives at that point. Anywhere on this side of C, you can have a derivative. And anywhere on that side of C, you can have a derivative, but not at C, because there's the value at C, and you have a limit as you come this way of that, limit as you come this way of a vertical line. Never going to be the same. Okay? So that leads to theorem 4. Only in your book it's theorem 6. Okay, because the new edition had 2 theorems before 1 on this one. Okay. Now this almost feels like a jump discontinuity too. But here's what the theorem is. If a function is differentiable, it's got to be continuous. Differentiability implies continuity. Because if you can take a derivative of it, you can have a jump discontinuity in it. We just saw that. But don't take this too far. Continuity doesn't always imply differentiability. Okay, and we're going to get to this later. But let's just deal with the theorem 4. If a function is differentiable, it's got to be continuous. That implies that it is a continuous function. So if f is differentiable at some value x equals c, then it has to be continuous at x equals c. But do not go the other way. Just because it's continuous at x equals c doesn't always mean it's differentiable at x minus c, at x equals c. Okay? And we'll get there, I think, in a minute. But if we don't, let me go back to this one. Let's say, since they have this drawn here for us, let's say we had a function. I don't know why my pen. Okay, here we go. Let's say that this left-hand side of this function did something like this. Okay? Now I'm going to blow that up. Boom. Here we go. Boom. There. Now, ignore the dark line here and use my dark line. This function is continuous because it's defined as x approaches c from the left, it's approaching this value, as x approaches c from the right, it's approaching this value. But guess what? It's not differential. Just because it's continuous doesn't mean it's differential. Because this has a slope that's approaching here from the left and approaching there from the right. The slopes are not continuous, therefore it's not differentiable. So differentiability does imply continuity, but continuity doesn't guarantee differentiability. Okay? Now, I like to use, I've used it already when I talked about polynomial functions, when I talked about exponential functions. I mentioned 2 words, smooth and continuous. That is not a smooth function. It comes up here and then makes a jag down here. Not smooth at all. Okay? Now, it looks like if you raise this function up here and had it being smooth there, that could have been a differentiable function. Even though it might be defined, because to be differentiable, the derivative from the left has equal derivative from the right. continuity is only the function from the left equals the function on the right. So they're not always the same. Okay. Yeah, we weren't going to hit that, sorry. Okay. So let's move to what? Okay, that's another page away. So let's go back and do example 9. Why did I waste my breath? Here's one. Show that f of x is equal to absolute value of x. Okay? You tell me something about that function. Anything you know about absolute value function? Always positive, very good. That's why I put a very little negative down there. Okay. What else can you tell me about absolute value function? I don't know if you've hit this. I think you should have, but I don't think they emphasize it anymore. This, by the way, is a piecewise defined function. Guess where the piece has to be defined at? Where do things change in an absolute value function? At 0, exactly. So this is going to be some value when x is, where you want to start? Less than or greater than? I don't care. Greater than. When x is greater than, you want the equal sign with that one or the other one? I don't care. Yay or nay? Huh? That one, okay. X greater than or equal to 0. And then it's going to be defined slightly differently from x less than 0. Okay? Now, what are those definitions? Those are the parts of the domain we're dealing with. What is the function f of x equal absolute value of x when x is greater than 0? What function would it be? Give me a value greater than 0. 20? Is that what you said? Huh? 1. Okay. What is your absolute value of 1? Okay. So at 1, it will be 1. Okay, got it. Another one. 2 will be, absolute value of 2 is 2. Okay. What's that? Okay, at negative 1, what would the value be? Positive 1 again. You do another negative. Negative 2 would be positive 2 again. Okay? Now that's not really enough points to tell, but wouldn't you agree with me? This is what I was trying to fish for this earlier. That's what the absolute value function looks like. It looks like a V. Y'all knew that, didn't you? But you wouldn't tell me, would you? Okay. Made me work for it. Okay? Now let's look at the right-hand side of that V. If that's all you had, what was the function that would match that graph? Second? No, don't go that far. Just a function that will, now, that's supposed to be a straight line, okay? Y'all are making fun of my graph function, okay? That's just a line. What function would describe that line? Y equal x. Y is equal to x. The m is 1. The slope is 1. When x is 1, y is 1. When x is 2, y is 2. When x is 17 million, y is 17 million. Y is equal to x, right? Okay, so that's your first half of this function is equal to x. What is it on the other side of 0? When x is negative 1, y is positive 1. When x is negative 2, y is positive 2. When x is negative 17, y is positive 17. So what would be the function here? Negative x, exactly. Okay, there we have it. Okay? That is your absolute value function always. It's x when x is greater than or equal to 0, negative x when it's not, when it's less than 0. Okay? Now, that's a continuous function. Because at 0, it's equal to 0, right? Continuous function there. But what's the other thing you can tell me about it? What's the derivative of this function? F prime of x. And let's take f prime of the right-hand side. What would that be? F prime of x is what? You take a derivative of x, and what do you get? 1. That's anytime x is greater than or equal to 0. Take the derivative of negative x, and what do you get? Negative 1, anytime x is less than 0. Right? Is that continuous? What is it at 0? Second, okay, x equals 0, the slope is 0, but just to the left of that, what would it be? Like, negative 1. So it's negative 1 down to, no, the slope isn't 0 there, the slope is 1, sorry. Slope is 1 at 0, and just to the left of 0, it's negative 1. Is that continuous? Okay. I'm going to draw that function, okay? This function, the derivative function here. When x is less than 0, it's negative 1. When x is greater than 0, it's 1. Is that a continuous function? I think not, okay? Jump discontinuity, you can't get rid of it, okay? So guess what? Just because absolute value of x is a continuous function, the function is continuous. The limit of f of x as x approaches 0 from the left is 0. As it approaches 0 from the right, it's 0. The function is defined at 0. But its derivative is not defined at 0. Because it approaches 0 from the left, it's minus 1. Approaches 0 from the right, it's positive 1. What is it at 0? Undefined. There is no limit there at x equals 0. Okay? See that? Okay. Now, rehash. Differentiability implies continuity, but continuity doesn't always imply differentiability. Has to be continuous to be differentiable, but just because it's continuous doesn't guarantee it's differentiable. Okay? Now, another way to approach this, that's one way. Another way to approach it is the concept of local linearity. Okay? And that's what the next slide is showing us. Okay? See if I can zoom in on all this at once. I think I can. Okay. Here you have a function. I don't know what function that is. I don't even care to know what function it is. But I'm going to look at the function right here, that value there. And I want to know, number one, I can tell it's continuous. What I can't tell if it's differentiable or not. Okay? So I'm going to zoom in on this. Because guess what? This tangent line actually touches here, crosses there, you know, that's fine, it can do that. But it's, you know, it's, so how can I tell if this function, if that tangent line really does fit the bill? Well, let's take this function portion and blow it up. And when you blow it up, this is the same as this, but close to it, you get this, okay? This is still curving away here and curving a little bit away here, okay? So let's take this portion and blow it up. Well, this is awfully close here, separating a little bit. You still get some separation there. Let's take this portion and blow it up. And guess what? I can't tell a difference. That looks like a line, doesn't it? That then shows that your tangent line does exist, okay? if no matter how much you blew it up, you still had deviation there, that means that the tangent line isn't really there. This is what we mean local linearity. The graph looks more and more like the tangent line as you zoom in closer and closer to the point. So in other words, as you get closer and closer to the point, does that tangent line almost merge in with the function line itself? And if you get small enough, if it does, then the tangent line does exist. And if the tangent line exists, then you've got differentiability. Are you really going to do that ever? I don't think so, but it's a conceptual way to think of it. Okay? Let's go to that absolute value function we were just looking at. And let's see if we can make that locally linear. I think not, but let's see if we can. Okay? So here's the absolute value function, right? Let's zoom in on that. Okay? When you zoom in on that, it looks like that. Let's zoom in on this. Zoom in on that. It still looks like that. And no matter how much you zoom in on, and zoom in on, and zoom in on, you're always going to have continuity, sure, but not differentiability. Because the limits of the first derivative are different from either side of that. No matter how small you get, it will always look like that. Never become a straight line. Ever. Anywhere close to it. Okay. Does that make sense? All right. Now, here is a situation you'll run into sometimes. Okay? This would be locally linear, but yet the tangent line, it's sort of tough. The tangent line to this graph, okay, f of x is equal to x to the 1/3. Okay? Here's, and what this is the cube root of x, right? That's what that means. If x is negative, it's coming like this. It's equal to 0 at 0, and it's continuous at 0. And here it actually is even smooth at 0. But the problem is, what is the tangent line there? Vertical. Can you give me the equation of a tangent line that's vertical? X equals 0. Yeah, that would be this one. X equals 0. Or x equals 7. Or x equals 8. What's the slope of that tangent line? You think it's 0? That means it's horizontal, doesn't it? I thought we just said it's vertical. Okay, what would be the slope of this line, approximately? One. A little bit greater than 1. Maybe 2. 3. Ah! A vertical line would be an infinite slope, which is not really a number. But how do you know that's not a negative infinity? It may be going down, not up. But you don't. It doesn't exist. Okay? It doesn't exist. This line does not have a slope. A vertical line does not have a slope. And what gives that away? What might we do to check that? If I say find the tangent line, what is one thing we're going to do? Say again? You will, but what was your answer before? Okay, did I go over Children's Church with y'all? I'll take a derivative. Very good. Okay, here's your function. F of x is equal to x to the 1/3. So let's do f prime of x. How would you do that? Of course we know how, don't we? What would that be? It's a power function. Say again? Okay, I know there's an x there. Good. 1/3 x to the negative. What are you subtracting from it? 1. And when you subtract, second, negative 2/3. Because 1 is the same as 3/3, right? Right? So 1/3 minus 3/3 is negative 2/3, right? Okay. So there it is. All right. Now, there is your first derivative. That represents the slope of the tangent line at every x you can give me, except 1. Well, help me write that in a different way. I don't like negative exponents, but in this case I don't. So write that for me without a negative exponent. How would that be? 1 over 3x to the 2/3 power, right? If you want to change the sign of an exponent, move it either upstairs or downstairs, wherever it was, move it another place, and move the minus sign, right? Now, if I were going to pick some values here, I'd say x equal 1. I can do that. What's 1 to the 2/3 power? 1, okay? 3 times 1 is? So the slope would be, they don't show that on here. That would be 1/3, okay? Now this scale is not very good because there's 0.3, there's 0.1, and there's 0.5 there. So the scale is not here, but anyway, they blew it up some so you can see that. Okay, I would also maybe choose a 8, when x equals 8. I can do that because I know what the cube root of 8 is. It's 2 squared is 4, and this would be 1/12. So it's very, very narrow slope when you get out to 8. Negative 1, we could do that too. What's the cube root of cube root of negative 1? No, negative 1. The cube root of negative 1 is negative 1, right? Negative 1 cubed is negative 1, right? So it'd be negative 1, but then you square that and you get 1, and 3 times 1 is, so again, at 1, they don't show it here, that would be a slope of 1. I mean 1/3, okay, 1/3. And then you go on out and it becomes negative 1/12. So it's always a positive slope. It's positive slope here, here, here. And it gets very positive here. Very positive here. And then it's positive from here. From very positive to becoming less and less and less positive. But always positive, except what happens there? At x equals 0. Cube root of 0? 0 squared is? 3 times 0 is? And 1 divided by 0 is? Undefined. There is no slope there. It's an undefined slope there. So that's what lets you know the tangent line doesn't exist. If you can't define the slope of a tangent line, it doesn't exist. Here's the problem, folks. It's a continuous function. It's a smooth function. It's locally linear there. But the problem is the vertical tangent line. You can't have a vertical tangent line. I mean, you can have it, but its slope is not defined. Therefore, the first derivative is not defined. So just because it's smooth, continuous, it still may not be differentiable at a point where you had a vertical tangent line. And that's the point. Okay? Now, they love these kind of functions. As a final remark, we mentioned that there are more complicated ways for a function, a continuous function, can fail to be differentiable. It fails to be differentiable if it's not smooth, like an absolute value function. That's not differentiable, even though it's continuous. This one's smooth, but if you have a vertical tangent line, it's not continuous. And they love these, don't they? Okay? They love these. I found them totally obnoxious, okay? Here's the graph we're talking about. Okay? The graph of f of x is x times sine 1 over x. Okay? Now, what gives it away that this is not going to be a differentiable function? This is not defined at all. At x equals 0, you cannot. Any other x, yeah, that's perfectly fine. But that's not defined at x equals 0. Okay? It goes faster and faster and faster between, as x goes closer and closer to 0, this is going to, from the right hand side coming in, 1,000, 1,001, 1,002, 1,000, 10,000, 80,000, whatever. It's just getting a bigger and bigger number, and of course, vibrating between any two, it always stays between plus or minus 1, except as x is smaller, you have an envelope here, and it gets there. So sure, the limit exists of 0, even though this is not defined, but how can that have a derivative? It can't possibly have a derivative, okay? And they pick out just some values here, and these are pretty small values too. No matter how small you got this scale, they always go look like that. And you pick a secant line here, a secant line here, a secant line here, a secant line here, and all the secant lines just, they never settle down. And you get closer and closer, they never settle down. Another thing is, the closer you get to 0, you'll find it's never, it's never defined at 0. You can't because it's 1 over x. But what's more, you won't find the slope will be linear either. Because no matter how far you get, it just keeps going crazy and crazy and crazy. The closer you get, the more rapidly it goes up and down. So that will not have a limit. Anything that looks like this will not have a limit. So don't even worry with it. There is no limiting value for the slope of the secant line, so it can't have a slope of the tangent line. Okay, so first derivative doesn't exist. All that on things that can't happen, and I think you can look at them and tell them they can't happen. Now, are y'all interested in doing preliminary questions, yay or nay? You want some? Okay. Let's look at number 1. Let's see. I think that's the last slide, so let's go back. Let's look at preliminary number 1. What is the slope of the tangent line through a point 0? I can't write. Goodness gracious. Through the point 2f of 2. Okay, is that a point? Sure. 2 is your x value, and whatever, when you plug x in to the function, that'll give you your y value. Okay? If, and they don't give you the function here, all they give you is f prime of x is equal to x cubed. Okay? But they didn't ask for the value of f of 2. All they're asking for is the slope of the tangent line at x equal 2. Anyone want to hazard a guess? We don't know the function f. I can tell you what it could be, but we're not. That's a different course. All we know is f prime at x, at any value x. Can you give me the slope of the tangent line at that particular point? Even though we don't even know what f of 2 is. What is the slope of a tangent line related to? Yeah, it's the first derivative, isn't it? That's the whole purpose of this thing, right? So if we know there is a point at 2 f of 2, what's the slope there? How did you get that?
Because x equals 2, and then f of 2, which is basically y.
Okay, it's some value. It's not 2 necessarily. It's f of 2. We don't know what f is. Okay? But we know what? Huh? Yeah, we know what x is. What is x? 2. Okay, and what else do we know? Say again? F prime, which is the derivative. And if we know the x value, you know the slope of that value, don't you? And what would it be? 8. Perfect. That's 8. Feel like a dentist here, pulling teeth. This is 3.2. Let's make sure they got it right in the back. 3.2 preliminary, 8. Ding, 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 ding. Okay. Number 2. Evaluate f minus g prime at 1 and 3f plus 2g prime at 1, assuming that f prime of 1 and g prime of 1 is equal to 5. Okay? Can you give me any rule about the derivative of a difference? If you had to make a wild guess, didn't know a thing, what would you hope the answer would be? Derivative of a difference, you would hope to be all right. If you look right above you, okay, at that rules for taking a derivative, the third rule there, it has a plus there, but it works just as good as if there's a minus. What do we see that this derivative of a sum is? It's the sum of the derivatives, right? So guess what? If that's true for the sum, do you think that could be true for a difference? F prime of 1 minus g prime of 1? Yes, and it's true. Now can you give me an answer? If these are true? -2. You thought it was hard, didn't it? Pretty easy, okay? All right, so you evaluated that one. How about this one? What would you guess the derivative of 3 times one function plus 2 times another function is? What would you hope it would be? And these, by the way, are called the linearity laws, and they're true. What would you hope it would be? 3 f prime of 1 plus 2 g prime of 1. Wouldn't you hope that to be true? That the derivative of a sum of 2 products would be the sum of the derivative of the 2 products, right? And what would that be? Say again? 9 plus 10. Did you say 19? I couldn't hear. Okay, very good. Excellent. Okay. Let's make sure the back of the book got them right. -2, 19. Perfect. Good for that. Okay.
Will you essentially just plug it in?
Say again?
All you do is just plug it in?
Now you first have to use your what they call the linearity rules. First we'll start with the sum. Okay. That 3f plus ut, the derivative of the sum of a product of functions is the first step would be 3f prime, that's 3f prime plus ut 2g prime, both evaluated at 1. And then by the constant multiple rule, you can pull the 3 on the outside and make it 3 times f prime plus 2 times g prime. F prime is 3, g prime, yeah. So in that sense, you sort of are plugging it in. Actually, you're really mentally going through 2 steps there. Okay, but yeah, kind of. Okay, let's do number 3. To which of the following does the power rule apply? Here's A. F of x is equal to x squared. And B, f of x is equal to 2 to the e. To which one of those, or both, does the power, or neither, does the power rule apply? If you're taking a derivative. Huh? A, for sure. What is the derivative of f? 2x. What's the derivative of b? Say again? Not what? What is e? It's a number. And 2 raised to a power is a number. Right? And what's the derivative of a number? Say again? The derivative of a constant is 0. Exactly. That's just a constant. That's a number. 2 raised to that power, or that number is a number. And derivative of a number or a constant is 0. Okay. Power rule doesn't apply. That's the derivative of a constant. That's the very first one above. Derivative of a constant is 0. Okay. Let's make sure the back of the book got it right. Their answer is just going to be A. I can't find it. Oh, I'm sorry. There's C, D, E, and F. I'm sorry. There's more. I didn't see those. Okay, let's do C. F of x is equal to x to the e. D will be f of x equal e to the x. E will be f of x is equal to x to the x. And f will be f of x is equal to x to the minus 4/5. Okay. We got this one? Yes. This one? No. Okay. How about C? F of x is equal to x to the e. Why not? Second. What is constant? The e? Okay. Is 2 a constant? That's x to the constant. It's an irrational. Oh, because it's an irrational number, you can't do it. Is that what you say? And that would be wrong. Okay. Sorry. It's just a number. Square root of 2 is an irrational number. You can subtract 1 from the square root of 2. Give you 0.414, blah, 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 blah. Yeah. So this one, yes, you can. That's just a variable base raised to a constant power. Yeah, power rule applies. Its derivative, by the way, f prime of x would be Anyone want to hazard a guess? E to the E times x to the E minus 1. That's it. E's just a number. You can subtract a number from a number. Okay? How about D? Alpha of x equal e to the x. No! That's an exponential function, not a power function. Okay, so power rule doesn't apply. How about E? Okay. Huh? Oh, would it? Okay. What would it be if that were x squared? Two x also, wouldn't it? So does that mean x equal 2? I don't know what it means. No. That, again, that is not purely a power function nor an exponential function. It's a combination of the two. So it's still got, see, to be a power function, you must have a constant as the exponent. This does not have a constant as the exponent. Power rule does not apply. How about the next one? Yes, it is. Even though that is a rational number. Even though irrational numbers won't work. No, they will work too, won't they? Okay. So we got A, C, and F. And F. A, C, and F. What did they get? They said B? Did I write it wrong? They were wrong. Well, okay. No, they're wrong. Okay. B does not, power rule does not work. Okay, is that what you're saying? That's what you would say if the power rule did work. F prime of x. But you see, there's no x in there, okay? I thought I may have written it wrong, but I didn't. You say it would be e times 2 to the e minus 1, okay? No, it just isn't, okay? Because this is a constant. That would be, give me a constant. Make up a constant, any old constant. Second? 2. Okay. So, f of x is equal to 2. Okay? Now, couldn't I say that's 2 to the 1? Okay? And so, f prime of x then would be, and what's the derivative of 2? 0. Okay. But using the rule, let's call it 1's rule, okay? That would be 1 times 2 to the 0th power, right? And that would be, what is 2 to the 0th? Second, 1, and 1 times 1 is 1. So now, on the one hand, we say the derivative of 2 is 0, and by 1's rule, we say it's 1. Can it be both? So, which are we going to throw away? Let's keep 1. No. All right. Let's do number 4. I think I'm going to have to erase it. All right, to erase this? Okay. Choose A or B. The derivative, okay. The derivative does not exist if the tangent line A is horizontal, B is vertical. Says the tangent line, the derivative does not exist if the tangent line is horizontal or if it's vertical, one or the other. It does not exist if it's vertical because you can't define it. What's the derivative if it's horizontal? Okay, the function's a number. 0, the derivative is 0, except by 1's rule. No, never mind. Okay. All right. Let's do number 5. Which property distinguishes f of x is equal to e to the x from all other exponential functions, g of x is equal to b to the x. What property distinguishes f from g? Second? Okay, well, e is just a number. But what's special about f that's not always true about g? Say again? No, I mean, b can be any constant. Any constant. Derivative of f is f, right? Derivative of e to the x is e to the x. And generally, derivative of g is not equal to g because it has some factor. Remember that m of b that they did? That's not going to be 1. For e to the x, it is 1. So that's, I think, what they're looking for. I forgot to check their answers in the back. The line number 5, the line tangent to, no, 4 is b, and that's what we got. 5 is the line tangent to f of x equals e to the x equals 0, has a slope equal to 1. Okay. Yeah, and that's what f of 0 is. So I think, yeah, we both got the same thing. Homework exercises here. Do any of the odds 1 through 5? Do any, whoa, yeah, let's see. Have we gone over? No, we got time, okay. Okay, any of the odds 1 through 5, any of the odds 7 through 13, either 15 or 17 or both. Do 19. Then do any of the odds 21 to 31, either 33 or 35 or both. Any of the odds 37 to 41. Any of the odds, 43 through, wow, whoa, through 69. Now, I wouldn't just do 1 or 2 of those. I would do several of those in that group. Okay, then any of the odds 71 through 75. And now they say you need a graphing utility. If you can do it without it, try it with any of the odds 77 through 81. Then any of the odds 83 through 89. All right, and that does it for 3.2. Now, I need a bladder break. I don't know if y'all do or not, but I need to run down 3.2. Okay. If not, section 3.3 is continuing our study of derivatives. We're now going to come up with a couple more rules. Okay? The first of these, well, the two of them are the product rule and the quotient rule. In the last section, if you remember, one example we did several of, the derivative of sum, tell me what that was. Derivative of a sum function is the sum of the derivatives. Derivative of the difference is difference of the derivatives. So, what might you think the derivative of a product might be? Not. Okay? That's where we run into problems. That's why it has its own section. And in fact, who are the two big creators or people who fought like cats and dogs over who created calculus? Newton and who? Newton was one. Leibniz was the other one. Leibniz, okay? Now remember, Newton was such a picky person. He wanted to make sure he had everything just right before he published it. He refused to publish, he just put off till he made sure all of his I's were dotted and T's were crossed. Whereas Leibniz, on the other hand, published as fast as he can and see if he can beat Newton. Yeah, may not have been the reason. But he published something early on which said the same thing y'all did. The sum of a product of a derivative of a sum is the sum of the derivatives. The derivative of difference is the difference of the derivatives. And the derivative of a product is the product of the derivatives. Until someone said, no, it's not. Okay, and he went, whoops, made a mistake. Had to go back and retract. Newton typically would not have done something like that. But Leibniz was trying to scoop, trying to get along. Okay. Well, the product rule is different from what the sum and that's not what I want. From what the sum and difference rules are, because the product rule requires some extra steps. Now, number one, F and G both must be differentiable. If one of them's not, then don't even try, okay? The product will not be. But if F and G are differentiable functions, what are two conditions that usually will guarantee differentiability? Not always, but most of the time. Smooth and continuous. The only problem there, if you run into a vertical tangent, then you can't do that either, okay? But, so F and G are both differentiable functions. Then FG, the product of the two, is also differentiable, just like it was for sums and differences, except that the rule is different. And here's what the rule is. If you have the product of F and G, the derivative of that product is the first one, F, times the derivative of the second, plus the second times the derivative of the first. Except, since these are multiplied and divided, you can rearrange the order anytime you want to. You could have said derivative of the first times the second, plus the second times the derivative of the first. I mean, you can do it either way you want to, okay? Wait, I said that the same way. Derivative of the first times the second, plus the first times the derivative of the second. You can swap this order. You can swap these orders. It's fine. I mean, multiplication and addition are both commutative. So as long as you get it down. Pick one, take the derivative, multiply it by the derivative of the other, then add to that the derivative of the first times the second, or whatever. Okay. That's the product rule. And Leibniz got it wrong the first time he published it until someone corrected him. Okay. Now, usually I like to do the first time derivative of the second like they said here, but in your text, I noticed they put derivative of the first times the second plus the first times the derivative of the second. As I said, it doesn't matter as long as you got one derivative, either one derivative, the other not, and the other derivative, the one not, okay? And the plus sign in between, however you do that will be fine, okay? Now, they say they prove the product rule after presenting 3 examples. Let's just do the 3 examples, okay? Okay, well, let me back off. They don't give you any room for that. So let's do the 3 examples. Find the derivative of, let me get my pen activated again, okay? Find the derivative of h of x, where h of x is equal to x squared times 9x plus 2. Now, there's more than one way to do this derivative, okay? Let's do it using the product rule. So, using the product rule, what would h prime be? And you use it in whatever way you want to use it. X squared times 9, derivative of the second, right? Okay? Plus, no, if you did the first function times the derivative of the second, then the second time you do the derivative of the first times the second. Say again? To what? X times, no, 9x plus 2. Okay? 2 functions. This one times that one. The first times the derivative of the second plus the second times the derivative of the first. Right? That's the product rule. Okay? Now, because those are polynomials, let's clean them up a little bit. What would this be? 9x squared, right? Plus 18 what? X squared plus 4x. And what would that be? 27. Ran out of fingers. No, I'm just kidding. X squared plus 4x. Okay. Now this was a rather strange one to give you to do a product rule. And just in order to check and see if we got it right, I'm going to have you do it another way. First thing I want you to do is multiply that. Don't do a product rule for a derivative. Multiply that out. That's just a polynomial, product of two. What would that be? 9x cubed plus 2x squared. Now take a derivative of that. (27x squared plus 4x). And guess what? Same thing we got the other way, which should make us feel warm and fuzzy, right? In fact, I wouldn't be at all surprised if someone, when Leibniz did it wrong, they say, look, this doesn't work for simple polynomials. Whoops, you know, got it wrong.
Can we just do it the simple way?
What's that?
Can we just do that the other way?
You can. To me, this was sort of a bizarre problem because it was much easier to do the other way, I thought. But they were just trying to give you something as an example. Okay? Now, find the derivative of this one. Oh, and by the way, they got 27x squared plus 4x. Good for them. Okay. I don't know if I'm going to have room for this. So is it all right if I erase that? Y'all got it? Okay. Okay. Example 2. Find the derivative of y is equal to 2 plus x to the minus 1 times x to the 3 halves plus 1. Okay? So what we want is y prime. And let's use the product rule first, and then we'll see if the other way will be easier. Okay? Product rule first. How does that go? You want to do the derivative of the first? Okay. What is the derivative of the first? Second? Yeah, we can do that. What is that? 0, okay. That's the first part of the first. What's the second part? Negative x to the negative second. So that's the derivative of the first. And what do we do with it? Times the second, x to the 3 halves plus 1. What's next? Plus okay, you're doing the derivative of the second, that's fine. That would be 3 halves x to the what? 1 half, very good. That's it, the derivative, but what do we do with that? Times the first, which is 2 plus x to the minus 1. Okay. Now, if they leave it in that form, I think that's fine. They don't. Okay, so let's multiply these out. And this is just distributing. A little bizarre, but we can do it. Okay, what would the first term be? Negative. Say that again. X to the, think of this as negative 4/2, right? Times x to the positive 3/2. When you're multiplying same base, second, negative what? Third, is that what you said? I'd say a negative 1/2. Okay, because aren't you got the same base. Okay, the minus sign's the minus sign. Okay, then x to the minus 2 plus 3/2, right? Minus 2 would be the same as minus 4/2 plus 3/2 is minus 1/2, right? Okay. Good deal. That's the first term. What's the second term? Foiling. Not foiling, distributing. Minus x to the negative 2. Yeah. Times 1, it stays the same. Okay, how about the next one? Looks like a plus to me. Okay, I couldn't hear. How about a coefficient of 3? Is that what you, okay, 3 x to the 1/2 power. Very good. Last distributive is plus 3, well, it's 3/2. And then what do you say? X to the, I can't hear. How'd you get that? Did you say negative 1/2? Say yes. Okay, good. Okay, negative 1/2. All right. You see how you got that? It's the, okay, the coefficient is 3/2 times 1 is 3/2, right? And distributing this one times the last, right? This one, right? Then this one is 3/2 times x, so that's 3/2. And then you're multiplying x to the 1/2 times x to the negative 1. So when you're multiplying same base, different exponents, add or subtract the exponents. 1/2 minus 1 is minus 1/2, right? 1/2 minus 2/2 is minus 1. Right? Now, what can we do from that point? Are we done? So, like terms. And what like terms do you see? Ah, yes, those are like terms because they have the same variable at the same power, okay? And that gives us, those two combined gives us I don't think it's negative. This is 1/2, yes, 1/2 x to the negative 1/2, right? Minus 2 x to the minus 2 plus 3 x to the 1/2. Right? That's the answer I hope they got. Let's see if they do. They start with the 3x to the 1/2, which is fine, plus 1/2 x to the minus 1/2, which is fine, minus 2. No. Whoa. Whoa. Oh, I put in a coefficient that wasn't there. Okay. Where the woozle wasn't. Okay. Yeah, there it is. Okay. Y'all know where that's from, where the woozle wasn't? Winnie the Pooh. You should be doing your advanced reading, shouldn't you? Okay. Okay. Now, you want to try this the other way and see if it's any easier? Multiplying first and then taking the derivative? No, okay, I sort of agree with you. Y'all had so many troubles with your fractions, I'm saying let's not even open that can of worms, okay? But you could do it, and you take a derivative, you'll get the same thing. Okay. Good for you. Now, they actually did it, though. For the second one, they didn't do it for the first, but for the second one, they did multiply first and get it. Y'all need the experience of doing that or not? Let me know. Yay or nay? Nay, okay. We won't. Okay. Let's go on to example 3. I think I'll clean that. I think I could get it all on this page, but just in case not. Y'all got this one? God, I can erase it. Okay. Let's do the third. A different notation this time. We're doing d by dt of t squared e to the t. And guess what, folks? On this one, there's only one way. There's no multiplication you can do first. To do it, you have to use the product rule here. So, tell me what to do. Not where to go. Okay.
So dx over dx, d over dx, that's part 1, right?
Okay, say that one more time.
D over dx is the first.
Okay, that just means take a derivative. First derivative, right. Okay, all these three notations mean the same thing. Take a derivative. Okay? Take the derivative of what's in the parentheses there. Now, I admit my E is ugly and he's probably making fun of me, so I'll see if I can clean that up some. Okay? It's E to the T. Okay. Okay. Okay, now. Okay. That is a thing saying, take a derivative of that. It's just like if that was a prime out there. If you had named that F of t, you'd say F prime of t. Or if you had said y is equal to that, then take y prime. So that's just another way of saying take a derivative with respect to t.
So t squared.
Say that again. T squared. Okay. Now I hope there you took the first and did the derivative of the second. Is that what you did? Say yes. Yeah, okay, good. All right. Because that is, the derivative of e to the t is e to the t. I love it, right? Next. That's halfway there. No. 2t e to the t. Now, the e to the t's didn't change because the derivative of e to the t is e to the t, and e to the t is e to the t. So that part, those stayed the same. But the first one, this was the first time derivative of the second, which is that, plus the derivative of the first times the second, which is also that. Okay. Now, we can maybe simplify that a little bit by factoring out common factors. What will you see as a common factor? Say again? Okay. Also a t. T e to the t times, and what do you have left from the first term? T 2. Okay. I don't know if they took it the extra step or not, but you could simplify. I mean, I don't know if that's any simpler. It seems a little simpler. What's that? They only took the e to the t out? Then what's the point? I mean, why? If you aren't going to take out all the common factors, why take out any? And they left it at the end. It doesn't matter. And that's the I mean, that's the issue that I have with having these homework modules that you do, like Advanced Web Assign or these other things. They only going to give you credit for one answer. And this, I wrote a correct answer. The previous line was the correct answer. The way they did it was the correct answer. You could have put the e to the t in front of the parentheses. That would have been a correct answer. You could have put this t, e to the t behind the parentheses. That would have been a correct answer. And yet they would only mark you right for one of those. Or maybe they came up with another one. So, I spend more time, when I've tried using those, more time consoling my students, say, no, you did get it right. They just don't recognize that answer. There's nothing wrong with it. So I just don't even mess with it. Now, the next thing they do here is say this is a proof of the product rule, okay? It's sort of a proof. It's what you call kind of a geometric proof, okay? According to the limit definition of a derivative, and if I'm going to write, I can't blow this up, so I think I will write that f prime, let's see, how would I write that? I'm sorry. Okay, what you're starting with is the product function. What a pain in the neck this is. Okay. F times G. Okay. Now, this is a weird way of doing it, but it's okay. Picture this as F times G as a rectangle with length of F and width of G. And you're saying this product is this white rectangle here. So I don't see this as a rigorous proof, but it's okay. Now, the derivative of that would then be the limit as h approaches 0 of, now how does this go? F of, y'all forgotten how it goes, x plus h times g of x plus h minus f of x, g of x, all over h, right? The product function is what you're taking the derivative of, so that the f of x plus h times g of x plus h minus f of x times g of x all over h, okay? Now, if this is your product, okay, f times g, then what they do here is split this into two pieces. Here is your g of x plus h, there's there. Here's your f of x plus h, there. So basically your numerator, this part of the numerator is this big box, this big rectangle here, minus f of g, okay? So that says, now, there's no limit involved in this, yeah, okay? So that's saying the difference between this and that is this times h, okay? Now, if you look at what the difference is between the outer and the inner, this one up here is f of g, f of x plus h, which is this length, times g of x plus h, which is, that's that product here, okay, minus g, okay, I'm sorry. There's an extra parenthesis there. F of x plus h times g of x plus h minus g of x, that gives that length. So that's this strip here, okay? Now what this strip over here is g of x, that's the width here, times f of x plus h, minus f of x, so that would give you this one, okay? Now, if you take those separately and let this basically right here over h, this thing right here over h is g prime, right? This part here over h is g prime, so this would be f times g prime plus, and this would be g, and this part over h would be f prime. So that then is f times g prime minus plus g plus f prime, and you see you do get the whole rectangle there. Is that very satisfying? Not to me. If you find it satisfying, hang in there and go for it. Okay? Now, here's what else they're going to do with that. Okay? Keep sort of the picture in mind, and this is what they did. I'm going to blow it up so you can see it better. To me, the picture, though it's sort of interesting and stuff, I have to think what the answer is to work back to get what the picture's trying to tell me. So this says the product of f and g prime is this product, and if you think back on the picture, that's your f of g plus h times this thing. Now, they had left off the dividing by h, which had to be in the limit, so they're just going to put it under this part. But that part there that was g of x plus h, which is this way, minus g of x, that gave the width of that strip. You put the h under that, this is simply g prime, and that the limit is h versus 0, that would be just f of x. Okay? Plus, and again, same thing, the g of x, that was the width this way, times the difference of there, which would be f of x plus h minus f, and that would give you that strip there. Over h, that would be the derivative of f prime. So when I was doing the arm waving, that's what it's showing. And this, sure enough, is f g prime plus g f prime. Okay. Yuck. I guess we're out of time. And that just carries on and does the same thing I just said. And what we will go down to, we'll start next time with the quotient rule, if I can find my pencil. Okay. Okay, we'll start next time with the quotient rule. But this has allowed us to have a few more homework exercises. You can do any of the odds 1 through 5 and stop there. We'll do the rest of those next time. Good deal. And next time will be next Monday. Wasn't it great having 2 classes in 1 week, finally? Yes, that made it so much better week, didn't it? Yeah, I thought so. You had to say that, didn't you? All right, good deal. We'll see you. Have a good weekend. Working on those tests and research papers, right? And cleaning house. Okay. Okay. Good deal.